In this lecture, we're going to introduce this notion of simple functions. I think if you have taken PMATH for 50, you'll remember the way we define the Lebesgue measure is by first using the simple functions to approximate a measurable function. And you can also compare this with the idea of in the Riemann integral, you're really using a Riemann sum. So the Riemann sum is basically you pick one specific number on each of the interval, and it's essentially you're integrating a simple function. So this is kind of the same idea if we want to define the integration in general measure spaces. All right, before we go into the detail, I just want to briefly introduce this notion of a function algebra. It will be quite important concept later on if you move on to functional analysis and operator algebra later on. So here's the definition. So suppose I have a collection of functions. So here the functions are all from some space X to let's say R or complex number or something else. Okay. This collection, we call it a function algebra or a algebra of functions. First of all, it is a vector space. So basically a vector space will mean that if you take any two elements, F and G inside your collection, and you take some kind of scalar, in this case, let's take real, the F plus lambda times G will also be inside your collection. Okay, so that's what I mean by a vector space, following the usual addition, pointwise addition, and the scalar multiplication. And the algebra also is equipped with another operation, which is a associative and multiplicative map. We call it the star here. So basically, if I take two elements in this function algebra, then I compose them using this multiplication map, then I get something inside this collection as well. And if I can find these two conditions, then this collection is called a function algebra. Okay, so here's the function algebra. Okay, so if you taken some algebra course like a ring theory or field, you probably notice this F, it just in pure algebra sense is also called associative algebra. Okay, so the multiplication is the associative map, and you have a vector space underlying vector space. All right, so the goal is to, in this first video of this lecture, I just want to show, because we have a notion of an algebra of sets, and now I'm also introducing an algebra of functions. I just want to show that they're somewhat related, okay? So to do that, let's clear up some notations. So here is the standard notation we will use. So suppose I have some set X and I take a subset A. Then I denote the indicator function chi of A. So here the looks like X is the Greek letter chi. So chi of A is essentially this function defined on X to real or complex, if you like. You just basically say the chi of A evaluate at the point X. It will give you a value of 1 if this point is a member of A, and it will give you a value of 0 if X is not in A. So it's really the indicator function. So this is the main proposition I would like to prove. Suppose you have a collection of subsets in X, let's call it a curly A, and you consider the linear span by those characteristic functions of elements in A. So let's call this F. You equip this F with a multiplication map, where just multiplication is just the pointwise multiplication. Then if this A you start with is an algebra, then this collection F is actually a function algebra. So let's prove this. So it's really simple. So this collection, first of all, because it's a linear span, it is a vector space, so that comes for free. This is a vector space, right? Because you're basically doing the span, and span is a vector space. So you're really just need to show this is a function algebra. Basically, you have a multiplication map. In other words, you need to show that For every two elements, let's say F and G that's contained in this curly F, then you have their pointwise multiplication is F times G. Okay, so let me remind you, this is simply defined as fx g of x. Okay, this is also inside F. Okay. All right, to show this, well, because it's a linear span, I'm only requiring to be I'm not taking any closure, so this is really just a finite linear combination. So each of them can be written as a finite linear combination. Let's say F is equal to some linear combination of AI times, I have too many A, maybe I should say alpha I, times chi of some set, say AI. And then G may be some other linear combinations. Let's say I going from 1 to n of some beta j. Let's use j, and maybe I should use a different index. Let's say chi of some b of j, where each of these AI and b of j, they are both coming from this collection A. All right. So I need to show that this F and G, their pointwise multiplication is indeed again in F. Okay. So how do I show that? Well, we just compute F with multiply G, evaluate at X. Okay, so this is essentially their pointwise multiplication. So this is I going from 1 to n of alpha I, chi of AI evaluated X. Okay, and then I multiply the thing I put in for G. So this is beta j of chi bj of x. Okay, and you have a double summation. You just make it multiply together. So I make it a double summation over I and j, where you have some scalar alpha I beta j of you multiply this AI of x times chi of bj of x. Okay. All right, then now you basically need to show that this multiplication is another indicator function or characteristic function of some sort, and it's fairly simple if you recall your PMATH 450, or if you just do observation. So here chi of AI of x, chi of bj of x. Well, if you think about what's the possible value it can take, well, it only takes a value of 1 if x is inside both AI and bj. Otherwise, one of the chi will give you a 0, so it will give you 0 otherwise. Okay, so essentially what you proved is that this is the same as the indicator function of AI intersect bj. Okay, bj of x. All right. So now you can show that f with g, the pointwise multiplication evaluated x is no other than this double summation of some scalar. So this is some scalar multiplied by this characteristic function of AI intersect bj. Okay. And this is again a linear combination, a finite linear combination of these characteristic functions. And because A is an algebra, each of these intersection is again a collection in A, okay? So I have this is also a linear combination of them, so it's inside F, okay? So F is an algebra. So essentially here, I'm really just using the fact that A is closed under intersection, okay? So technically that is sufficient for this F to be an algebra. So what is so special about this function algebra generated by an algebra? I would like to point out a remark in the end of this video. So when you have an algebra, then of course everything can be written as a finite linear combination of these characteristic functions, let's say alpha I chi of AI. And when you have an algebra, you can actually assume that these sets AI are disjoint, okay? So the idea is fairly simple. So let's maybe draw a picture so it will be a lot easier. So suppose you have some A1 and maybe you have A2 and you have some A3, they may not be disjoint. But as you can see, you assign a value of alpha 1 on this A1, so everything inside alpha 1 give you A1, and alpha 2 give you A2 give you alpha 2, things in A3 give you alpha 3. So if you have something that's in the intersection of alpha 1 and alpha 2, you're actually assigning a value of alpha 1 plus alpha 2. And the same goes with the intersection of two of them, A1 and A3, or A2 and A3. You add their corresponding alpha. And for the thing that's in all of them, you basically add 3 of the alpha together. That's what the function takes value on each of these sets. And because A is an algebra, you can just, each of these intersections is in fact in A, and you can take their set difference, that's also in A, and you can break this summation of alpha I chi of AI into these characteristic functions of their intersections. Okay, and that way you can make them disjoint. Okay, so more rigorously, what you can do is the following. It's one of my favorite tricks actually. So for every subset, let's say U contained in 1 to n, you can define a set, let's call it A sub U. That's basically all the x where x is inside in AI for all I inside this U, and then x is not in AI where for all I is not inside U, okay? So this A of U is basically contains the intersections of all the AIs where I is in U, and the complement, the intersection of the complement of those not in U. Okay, so you can really say this is just intersections of I inside U of AI, and I intersect all the let's say J in U complement of the A J complement. Okay, so apparently because A is an algebra, each of these AI and AJ complement is in the algebra, and so is their intersection. This is a finite collection. So I have this is in A. Okay, and you can prove the following. This is a fairly easy proof. Each of these AI, okay, so maybe I should say chi of AI, is no other than the summation of you sum over all the U contained in 1 to n, and you require the I is inside U, okay? And you sum over all of them, and you sum, let's say, chi of a U, okay? So they will give you the chi of AI, okay? So basically you break this chi of AI into a collection of chi of a U, and clearly these chi of AU, this AU are disjoint. These AU, this U contained in 1 to n, they're all disjoint. Okay, so in other words, this f of x equals to the summation of alpha I of chi of AI. Each of these AI can be broken into these U, so you can rewrite this as the following summation. So you can rewrite it as a summation over all the U, a subset of 1 to n. And let's just say beta of U times chi of A of U, where this beta of U is the summation of all the U where I is inside U of these alpha I, okay? So I'm not going to go into the detail, but this is some facts you can prove as an exercise, and it's one of my favorite facts. In fact, it's quite useful later on. All right, so we finish the proof of this remark. So basically, when you have an algebra, then the linear span of these characteristic functions, you can really just assume they are disjoint subsets, okay? And of course, you will rarely see an algebra later on in this course. So because sigma algebra is also an algebra, later on in this course, you will, of course, This also holds true when this curly A is a sigma algebra, and that's what's going to happen most of the time, all right?